In experiment 5, we're given some unknown. It's going to be an unknown KClO3 mixture. And so what's in the unknown mixture is KClO3 plus inert solids. The inert solids aren't going to react. And so what we want to figure out with this mixture is the percent composition. We want to figure out the percent KClO3 by mass. The percent KClO3 by mass is we need to figure out how many grams of KClO3 are in there over the total mass. The total mass is just going to be the mass of the unknown. And so let me just write that, the mass of the unknown. Times 100%. The mass of the unknown, we're just going to weigh this on a balance. The mass of the KClO3, we're going to determine this in two ways. The first way we're going to determine the mass of the KClO3 is by taking our reaction mixture before heating, and then as we heat this, what's going to happen is the KClO3 will begin to decompose. The inert solids won't. When the KClO3 decomposes, you have KClO3 solid with some heat and some catalyst. The catalyst is just there to speed things up. That's MnO2. The MnO2 doesn't really participate in the reaction in the sense that it's consumed or produced. It participates as a catalyst. When we heat, we end up forming KCl solid plus 3/2 O2 gas. All right, what type of reaction is that here? Is that metathesis? Oh, it's a redox, yeah, you're right. This is a redox. We can tell it's a redox because the oxidation states. The oxidation states change in the redox reaction. And so over here, potassium's +1, oxygen's -2, chlorine's +5. On the products, we have +1 for potassium, -1 for Cl, and 0 for oxygen. And so the chlorine went from +5 to -1. How many electrons does chlorine have to gain to go from +5 to -1? 6 electrons. So chlorine took 6 electrons, but who did chlorine take 6 electrons from? Oh, so chlorine's the oxidizer, but who did chlorine take the electrons from? Yeah, in this case, there's no other species. Oxygen normally is pretty happy with 2 electrons, right? But chlorine's so unhappy that it actually oxidizes its neighbor, what it's bonded to. If there's something easier to oxidize, it would oxidize that for sure, like sugar. We mix potassium chlorate with sugar. Potassium chlorate had no problem oxidizing the sugar. But in this case, there's nothing to oxidize other than oxygen, so by heating it, we can get it to decompose like this. And so oxygen's going to lose. We got 3 of them. Those have got to lose a total of 6 electrons. And that's exactly what happens. So as we heat this, what's going to be observed is that the O2 gas is going to escape. And then once the reaction's over, then what we have is we have the product mixture. The difference between the reactant mixture and the product mixture is this. We started off with KClO3 solid plus inert. We end up with KCl solid plus inert. The O2 gas escapes out the top of the test tube. And so the difference here is if we take the mass of the product mixture versus the mass of the reactant mixture, the difference in mass is going to be the mass of the O2. So the mass of the oxygen that was produced is going to equal, because atoms are neither created nor destroyed, is going to equal the mass of the product mix minus the mass of the reactant mix.
Are we going to calculate the water, since we got heated up, are we going to calculate the vapor instead of include the oxygen too?
Water?
Since they're going to vaporize, right?
Hmm?
Since water going to be vaporized.
Water doesn't get vaporized. We're assuming it's dry. There's no water here. This is just solid. This is a solid reaction mixture, and this is air. This is, we're going to melt it when we heat it, but eventually we'll let it cool back down. This is going to be solid product mixture.
Okay.
And so the only difference between the two solids is the oxygen atoms are no longer trapped in the solid. The oxygen atoms are no longer trapped in the solid. The oxygen has escaped out there. Then the difference in mass here is going to be how many grams of oxygen we just lost. And so we're going to lose some mass. Well, how much mass? Well, the oxygen's mass. So if we have the mass of O2, we can go from mass of O2 to moles of O2 to moles of KClO3. This is using the mole ratio. It's a 2 moles of KClO3 to 3 moles of O2. And then from moles of KClO3, we could get the mass of KClO3. From the mass of KClO3, we'll just plug that back into here. And we'll be able to calculate our percent KClO3 volume. So that's the easy way of determining how much O2 and how much KClO3 is generated. This would be a very short experiment, but what we're going to do, this is method 1, so this is the first way. In method 2, which we're just going to run one experiment, we're going to do both methods. Rather than letting this oxygen escape into the lab, you know what we're going to do is we're going to trap it. Trap the oxygen. If we trap the O2, then we can do this. We're going to, if we trap the O2, we are going to measure the pressure, the volume, and the temperature. And if we know the pressure, volume, and temperature, then we can determine the moles of O2 because it's a gas. It's just equal to PV over RT. If we have the moles of O2, then we can just go from here. Moles of O2 to moles of KClO3, moles of KClO3 to mass of KClO3, and then figure out the percent KClO3 mass. And so there are two ways to determine how much oxygen is generated. One way is the mass difference in A. The second way is to actually physically trap the O2 and measure how much O2 was generated. All right, in order to do this experiment then, this experiment requires a lot of measurements. One, you'll get an unknown sample like this. Unknown number. This is our KClO3 mixture. You know, it's KClO3 is a white solid, then it's mixed with some inert white solid. So this is it. We're not going to use the entire sample. We're just going to use around 1.5 grams. And so you're going to get an empty test tube like this. We need to know the weight of the test tube. And so to get the weight of the test tube, it says to get a wire and hang the test tube on a balance. You know, we used to have these old style balances like this, where you hang one mass over here and then you counterbalance it with weights until the two are the same. We don't have those balances anymore. The procedure was written for that style of balance or the other style of balance. The other style of balances were unable to tear heavy objects. If you can't tear heavy objects, then you can't use a beaker like this to hold your test tube. You know, what we're going to do, however, is we have these very expensive balances, these $15,000 balances. And so those are capable of tearing heavy objects like a beaker. And so we're just going to take a beaker and tear it. And then we're just going to weigh our test tube, empty test tube. But our balances are so sensitive that they are affected by fingerprints. Do you guys know? It's okay to touch the beaker because we're going to tear it anyway, but the test tube, we want to wipe off our fingerprints from the test tube. Is that clear? So what we're going to do is we're going to have a lot of different weights. We need the weight of the test tube alone, empty. And then we need the mass of the test tube plus our unknown. Okay, we'll have to record that, mass of test tube plus unknown. And then we're going to get a little spatula full, actually about a match head's worth of MnO2. So just get a 1 or 2 match heads worth of MnO2, which is a black powder that's our catalyst, and put it in there. And then reweigh it. And so we're going to have the mass of the test tube, the mass of the test tube plus our unknown, and the mass of the test tube plus our unknown plus the MnO2. We need to know what everything weighs. You don't want to use the entire sample of unknown because it's probably going to be too much. Okay, then we're going to set this up. So we'll use a utility clamp here to do this. I don't know.